Hi, I'm Brian Nolan. This is Calculus and its applications, and this is the last of 3 mini lectures on the foundations topic of linear equations and their graphs. So in this last mini lecture, I'm going to look at the topic of simultaneous equations. Now, this is important because we have lots of situations in science, for example, in electrical circuits and physics, balancing chemical reaction equations, where we come across situations where we have two unknowns, two variables, and two pieces of information about those unknowns in the form of linear equations. So this sounds like a situation that we should be able to deal with because we have two things we don't know, but we have two independent pieces of information. So we're going to see how to extract the value of the variables from those two equations, from those two pieces of information. Okay, so what it gives us is what we refer to as simultaneous equations because we have two equations that hold true at the same time. They're simultaneously true. And our only learning outcome here is to solve pairs of simultaneous equations. In other words, we have two equations and two variables. Okay, now we can think about this problem either geometrically or algebraically. So I'm going to just say a few words about how we think about this problem geometrically and then look at an example that involves algebra. So we look at everything through the medium of examples. So let's consider this situation here. So it's phrased in abstract mathematical terms in terms of x's and y's, but let's bear in mind that in applications, these x and y's will represent quantities from science that we need to know the values of. Okay, so the question is as phrased, we want to find the values of x and y if x and y simultaneously satisfy the equations 2x minus 3y equals minus 4 and x plus 6y equals 9. Now, as I said a moment ago, I'm going to think about this problem geometrically. So the way we can solve this is by drawing the graphs of both of these lines and identifying the coordinates at their point of intersection. Because what we want is an xy, a pair of values xy that satisfy this equation. In other words, they lie on this line. And the xy values we're interested in also satisfy this equation. So they also lie on this line. So we're looking for a point that lies on this line and also lies on this line. In other words, we're looking for a point of intersection. Okay, so I'm just going to display the solution here. What I've done is I've identified points, 2 points, using some algebra. I've identified 2 points that lie on each of the two lines. So for the first line, I let y equals 0 to give me the value x equals minus 2. I let x equals 0 to give me the value y equals, what is that? That looks like 1 and a third perhaps. And I have those 2 points, and then I can take out my ruler and join those 2 points to get the first line. Then I do the same thing for the second line. I identify 2 different points that lie on the line, and I use a ruler to join them up. So then I can solve the problem geometrically by simply noticing that the point of intersection is, well, the point that I can see here. Okay, so there's my solution in some sense. I've completely solved this problem now. I found the point of intersection. But of course, what I want are the x and y values. So I need to read off from the diagram there. What are the x coordinates? Well, it looks like the x coordinate, it looks like it's sitting exactly on this vertical line here, which is at, looking at the values I have, there's 0.0, there's 0.0, there's 0.5. So this must be 0.1, 0.2, 0.3, 0.4, 0.5. So my x coordinate looks like it's 0.2. And my y coordinate, it's close to 1.5. There's 1.1, 1.2, 1.3, 1.4, 1.5. So it's most of the way between 1.4 and 1.5. So it looks like it might be round about something like 1.48 or so. Okay, so that's how I can solve a problem like that geometrically. But you can see the limitations because I have to draw a very, very careful diagram. And as you can see here, of course, I used some software to draw this, and I get a really nice accurate diagram. Doing that by hand, I lose accuracy. And I also lose accuracy by reading off from the diagram the coordinates of these points. So I'm fairly sure that my actual point of intersection is close to those xy values, but I don't have 100% accuracy there for my coordinates x1, y1 of the point of intersection. Okay, so that indicates to me that, an algebraic approach which would give 100% accuracy might be preferred. So let's look at an example from that perspective. We're looking at this situation here. We've measured the voltage across two different components of an electrical circuit. And that gives us these two separate bits of information about two currents that are flowing in these separate circuits. So we have these two currents, I1 and I2, and we find that they satisfy these equations. So the examples from physics, but we'll have very similar examples that crop up in chemistry and biology as well. So our two currents, our two variables here, so these are the X and Y, I1 and I2, they satisfy these two equations. We recognize that these have the form of linear equations because both equations take the form number times X plus number times Y equals a third number. Our job here is to find the values of I1 and I2. We're going to find them with 100% accuracy using fractions, and then just round off our numbers correct to 2 decimal places. Okay, so I'm just going to move over to another tool to work through this problem. Okay, so here's our example. Right, we have all of the background that's producing these two equations, but from the point of view of the mathematics, it's the equations that are the most important thing. So we have these two equations. I'm going to give them names. I'm going to give them very imaginative names of equation 1 and equation 2. Our job is to use these two bits of information that we know about I1 and I2 to determine the values of I1 and I2. And what we do is we're going to use an approach known as elimination. So going to use the idea that having two equations for two unknowns is all very well, but really what we really like to have is one equation with just one variable in it. And that's going to be something that we can solve immediately. Okay, so what I need to do now is look at these two equations and ask, is there a way of combining these two equations that would leave me with an equation where there is just one unknown rather than two equations with two unknowns? The process of elimination allows us to do that. And what it relies upon is the idea that if I take this equation here, if I take this first equation here and multiply both sides by 3, it's still the same equation. We're saying that this thing is equal to that thing. So 3 times this thing is equal to 3 times that thing. It contains exactly the same information. So we can exploit that idea to get rid of one of the variables. Now, the 8 and the 4 here have a nice connection. 8 is just 2 times 4. So if I had, at the moment I have 4 times I1 here, if I had 8 times I1, I'd be able to subtract there and get rid of the I1s and leave just I2s. Now I can't just willy-nilly change that to 8 times I1 because the I1 is sitting in this equation. But what I can do is multiply everything by 2. And that will still be the same equation because if this equals that, well, then 2 times this is equal to 2 times that. So that's what I do. I'll take everything in equation 2 and multiply it by 2. So what I'm trying to say there is I have 2 times equation 2. Well, what will 2 times equation 2 look like? I multiply everything left and right by 2. I'll get 8 times I1, which I like because I should be able to knock out the 8 times I2 there. 2 times 9I2 will give me 18 times I2. And 65 by 2, I believe, is 130. So there's my new version of equation 2. Now I'm going to write down equation 1 again. 5 times I2 equals 55. And really the idea here is that the information that's contained in those two equations is exactly the same as the information that's contained in those two equations. Now I can do my cancellation or elimination. If I subtract everything on the left from everything on the left here, well, then that must be equal to what I would get if I subtract this from that, because this number is equal to 55. That number is equal to 130. So that take away this is the same as 130 take away 55. Okay, so I'd subtract. So 8 I1 take away 8 times I1, that's 0. Then I have 18 I2 take away 5 I2 will give me 13 I2. And 130 take away 55, just be careful to check that. I think that's 75. Yeah, okay. So I have an equation now that's much easier to deal with because I have just one variable, the I2, and numbers. So I can immediately write down the value for I2. Okay, so the 0 times I1 isn't going to play any further role. So I can write down then that I2 is 75 divided by 13. I might be tempted to put that into my calculator at this point, but I won't because I lose that accuracy. So fractions are perfectly nice, friendly numbers. We'll just leave it in the form of a fraction. Okay, now I need to get I1. And to get I1, I can go all the way back to the start here and use the fact that in these equations, I now know the value of I2. Okay, I figured out the value of I2. So if I take the second equation there and use the fact that I know I2, what will I get? I'll get 4 times I1 plus 9 times 75 over 13 is equal to 65. So chuck that into the calculator. We find that 4 times I1, 9 times 75, that's going to be 10 times 75 will be 750. Take away 75 will give me 675, I believe. Okay, so I subtract this fraction from both sides and I get 4 times I1 is 65 minus 675 over 13. And when I tidy up that fraction there, I find, using the common denominator and my calculator, of course, I find, and just check this number yourself, that I get 170 over 13. So now I can divide both sides by 4 to get the value of I1. So I1 will be 170 divided by 4 times 13, which is 52. Now I have a common denominator there. I can write that as, so that's 2 times 26, and that's 2 times what? That's 2 times 85, I think. So that's 85 over 26. Okay, so I have my numbers for I1 and I2 in the form of fractions here and here. And I'll throw those into a calculator and see what they look like to correct to 2 decimal places. So 75 divided by 13. I get I2, 75 over 13. I'm coming down from here. I2, 75 over 13 is, it seems 5.7692307, blah, 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 blah. I1 is 85 over 26. 85 divided by 26 gives me 3.2692307, blah, 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 blah. And rounding off to 2 decimal places, then let's see, I'll get 5.77. The 69 rounds up to 7, and this rounds up to 3.27. So there's my answer. I1 and I2 rounded off to 2 decimal places. Okay, so that method of elimination is our key method that we use for solving simultaneous equations. And it relies on the fact that, as I've emphasized there to going through the problem, that the first 2 equations contain exactly the same information as the amended equations. And we make an amendment so that we can cancel out one of the variables using this elimination procedure. Okay, so that brings us to the end of these 3 mini lectures on linear equations and their graph and simultaneous equations as well.